Hello and welcome to Machine Learning from Data. This is lecture 23, and in this lecture, we'll talk about something that's known as support vector machines or SVMs. In specific, we will talk about something that's related to maximizing the margins within your feature space. So let's quickly recap before we begin. So until now, we've talked about linear models, a lot of that actually, and last time we looked at the comparison of the linear models with a nonlinear transform, that's this one. With the neural network and the K radial basis function network. And we saw that there were a lot of similarities. One major dissimilarity that existed was in this case, we cannot look at the data before selecting my transform, the nonlinear transform. And this phi, which was my nonlinear feature transform, was in some ways analogous to this v of j. And we figured that in the radial basis function, there was some similarity with this mu sub j, which is like selecting the centers. And so in radial basis function network, we had access to in some ways to the data, not the y values, but the x values. And so we were using unsupervised learning to get some kind of like initial centers based on which we were like deciding which one belongs to which one. And in linear model, we didn't have any access to data, but in neural network, if like we had appropriate centers, sorry, not centers, the nodes, all right, we could actually fit the data. And so this was like tunable, or like we could fine tune it as much as we would like. So meaning we can fine tune the features depending on our data. So that's what we figured last time. And one important thing that we found out was that this neural network generalizes the linear model by cascading layers of the perceptron. That's why it was so powerful. But we needed to regularize it due to high chances of overfitting. We looked at that and a few methods of doing it. Of course, regularization is a powerful method, and that can be applied to neural networks as well. All right. So today what we're trying to do is, instead of looking at the cascading part of like cascading the linear model, we'll begin with the linear model again, but think about its robustness as opposed to the cascading effect, right? So that's what a support vector machine is. It's more robust form of the linear model. And of course, we'll make some adjustments to the way we have defined things, in the sense that some notation will change, but the fundamental idea of a linear model will stay the same. Okay, so even before we begin deriving the math behind support vector machines, let's try to understand the intuition behind what this robustness means. What is the meaning of this robust? All right, so this is a very simple data set, as you can see, and we're looking at like given some linearly separable data, and you've like implemented this separator, right? So there can be multiple separators. So one could be this is the first one, the second one, and then the third one. All are perfectly separating my data and correctly classifying my points, right? So the question that arises is like, which separator will you pick? What is your intuition telling you? Which one of these separators will you pick? Okay, so here like there are three separators that classify the data correctly. So which one is better, right? Well, if I am thinking about this for some time, of course, the one that I'm inclined to pick, the intuition tells me that I should be picking this one, the rightmost one. And why is that? Well, I'm thinking this, if just like let's say I have access to the data, I can look at it. So just by looking at it, I can see this like separation between the points, and this separator itself is like pretty far apart. They are far apart, right? And so that's my basic intuition. Now, data in general, we know has measurement errors, right? So like thinking about this data space, if I can just like move these points a little bit here and there, if I allow some kind of perturbation, right? Allow some kind of movement from the original place where they are, right? Then maybe I'm thinking in terms of my intuition of like which of these perceptrons will allow me to tolerate the largest possible perturbation, right? So in this situation, I think it's this one, because here with a very small perturbation, this would just like cross the separator, and similar is the case here for this point. So this was like my intuition, and that's why I picked this right one, because I think it will allow the tolerance of error a lot, right? And so I can still get E in equals 0, like even if there is like some measurement error here, and so that's why I'm selecting the right one. All right, so now what we'll do is we'll see something like this here. What is this like robustness of my data essentially? So imagine that we have these like gray spheres, right? The spheres that you're looking at around every data point. These are nothing but error regions that I was talking about, like the error regions if perturbation is permissible. So basically these error regions correspond to the area until which we are correctly classified, until we hit the perceptron itself, the classifier itself. So the separator here, this one, with like bigger gray circles, a bigger error region, right? It allows like, or it can sustain or tolerate rather a bigger, a larger error than these ones, right? So these are also allowing some kind of errors. That gray region is the error region, but this one is allowing me the most amount of error, right? And this kind of forces me to think about regularization, like the ability to deal with noise, right? And what we said about like the ability to deal with noise and regularization was not to be misled by noise. So that's what regularization did. It like not let my it would not let my model go astray because of the noise, right? So here what we are saying is like somewhat similar, that if you can tolerate noise, you are robust to noise, which is like very similar to regularization. So here, if we can enable our perceptron to do this, then we are building a robustness within my model, right? And then I would say that my intuition of selecting like the one on the right hand side matches my learning theory in some ways, right? So being robust to noise, which is like my measurement error, is good because of regularization, and we've seen that why. All right. So this is about like my intuition. Of course, we will have a more mathematical form of talking about robustness soon, but let's try to view this error region through the lens of like this cushioned region, or like a thicker sort of boundary that separates them. So let me show you what I mean. So here, like this thing is representing somewhat a similar error region as these spheres were representing. Let me show you how. So notice this gray region, that's what I'm calling like a cushioned region, that's what it means. And more cushion means more robustness. So this you have like this thickness on either side of the perceptron, and then you're thinking, when does it hit the first data point, or how much can I enlarge the thickness until we reach the first data point on either side, on any side, right? So if we are like being able to fit a wider hyperplane is equivalent to like be able to tolerate noise in the data, because let's say my hyperplane was like this much thick, and not just like this line, right? So then I'm letting it also tolerate noise, which we haven't seen until now with a perceptron at least, right? And so this thickness, this addition of thickness, sometimes also known as fatness, that's what we call the hyperplane is fat, which means that this is letting it build robustness in it, right? And of course, we need to mathematically quantify this intuition of getting the widest possible cushion, because that's what that's why this perceptron is different from these two, right? So the maximum width that was possible here was this much, which is obviously way less than this one. And so that kind of matches our intuition, because this is allowing a lot of cushion, a lot of width until you hit the first data point. So this process of having this like fat a hyperplane, or thick hyperplane maybe, is the fundamental idea behind support vector machines. And this is also called the maximum margin hyperplane, right? Margin meaning the how much away it is from the first data point it hits. And of course, we want this cushion to be as like thick as possible. And so that's why the word maximum margin hyperplane. All right. So we will build the theory behind this, like that's what the goal of today's lecture is. But there are two important questions that come up. Of course, we understand the intuition behind why we are after this cushioned hyperplane, right? And so the first question that comes to our mind is, can we efficiently find this hyperplane, this fattest or widest or thickest, whatever you like to call it, separating hyperplane? Because like if you remember from our like discussion of the perceptron, and of course you've implemented the perceptron yourself, you know that finding one hyperplane wasn't as easy. I mean, it took us quite a while to understand that idea. And now we're talking about like find of the many, find the one that is the fattest or that is the widest. So of course, is it that easy? And then the second question is that is a wider hyperplane better than a thin one? Like, why is it really, like, mathematically speaking or quantitatively speaking, is a fatter hyperplane better than a thin one? Yes or no? So these are the questions, these are the two crucial questions that we are trying to answer while we are building the theory, right? And so let's begin with question number one. Can we find the thickest hyperplane, also called sometimes the optimal hyperplane, because optimal in the sense that how fat can we get, right? So optimal hyperplane. And all right, so can we find the optimal hyperplane that separates the data, right? And in order to, that separates the data, and in order to find that, we will have to understand the geometry of the hyperplane one more time. And why am I focusing so much on the geometry? Because all the derivations, all the math that follows is easy to follow if you can visualize it. But of course, it is applicable to other scenarios as well, right? So what we're trying to, let's say this is my data. This is what let me create some like simple data set. And so these are 2 points, just like 4 points, maybe not have this one. All right, so that's that. I think looks pretty consistent with the one we had. I'm not sure. Let's leave it like this. Okay, and so we have, like, let's say one separating hyperplane, right? And the thickness of, like, or the quotient of the separating hyperplane is the distance to the closest data point. So that's the first, like, I wouldn't call it a definition, but that's the first observation we have, right? And just to, like, kind of give you an idea that we will begin working with the, like, separable data, we'll begin working with that. But of course, we'll talk about what happens when the data is not separable, then what happens. Okay, so going back to what is this, like, can we find the fattest or the thickest hyperplane that separates the data? And as I said, we can understand this by understanding the geometry of the hyperplane. And the first thing that comes to my mind is, like, what is thickness? And thickness is of the separating hyperplane is the distance to the closest or the nearest data point. Okay. Distance to nearest data point, right? And so which in this case would be like something like this. This one seems like the nearest, or maybe this one, I'm not sure, like whichever one. This thing is something that we are trying to find out. All right. So of course, like, because the definition itself tells us the distance to the nearest data point. So how do you compute the distance to a data point, right? And if we are just like looking at this data set, the way we will represent like the data matrix and the target vector here, for example, is x equals, and let's say this is like my 0, 0 begins here, right? And so that's 0, 0, and that is cross, so I'm like calling the cross a -1. So my target vector for the value for that one is -1. And then let's say the second one, this one is 2, 2, again -1. Let's assume the other one is 2, 0, this one, and so that's +1. And 3, 0, that is +1. So this is some kind of a data representation for the data matrix and my target vector. So let's see now. What we have to do is, as I said, we need to understand the geometry of the hyperplane before even like jumping into it. And I'll make some updates to the notation to be consistent with what the textbook uses. And so let's look at that. And I'll have to kind of demonstrate what's going on. And so in three-dimensional space, in 3D space, we have the hyperplane that looks somewhat like this. Okay, so this is my hyperplane in three-dimensional space, and the distance from a data point, some x, would essentially be like when you have like some perpendicular distance from here. Okay, we'll jump to that later, but first let me talk about the notation here. So the equation of the hyperplane, and what is this hyperplane essentially? First of all, hyperplane is a set of weights. I've been talking about hyperplane a lot. Of course, we are familiar with that, but it's like a set of weights, right? That's what my hyperplane is. Now, earlier, whenever we were talking about a hyperplane, especially when we were discussing neural networks, when we were discussing even the perceptron, we had this augmented feature vector. Now, in the updated notation for support vector machines is that we are considering a non-augmented feature vector, although the weights, like the bias in the weights, will still stay, but we will denote it separately, again, to be consistent with the text. So that's why what we'll have is like, this is my input. And remember, this used to have like 1 and then x1, x2, but now we'll say x1, x2, x maybe d, right? And the weights will be not W0, but like W1, W2, and so on to WD. And we will have a separate term for the bias, which used to be my W0. And now I'll call it B as in bias, right? So now we have the extra thing that's here is that we have weights and a bias, right? So if earlier, and let me write it down here, earlier my h of x was the sine of W transpose x, the only thing that has changed now is that my h of x is going to be the sine of W transpose x plus b, right? And all right, so a change in notation in support vector machines, and that's because first, I want to stay consistent with what the textbook says. And we want to separate the bias in our discussion of support vector machines because like when finding the optimal hyperplane that we just talked about, the bias and weights are treated differently. So it's convenient to put them separately right away. All right. So in addition to that, so this is the equation of the hyperplane, and the way this like separates two regions, because of course there's a separating hyperplane, and the way it will separate is like W transpose x plus b greater than 0. Let's say this is the positive region where all positive values are there, and this is the negative region. And so W transpose x plus b will be less than 0 here, which tells me then of course W transpose x plus b equals 0 is the equation of my hyperplane, right? Okay, so this is like the notation around hyperplane. Now next we need to define what do we mean when we say that it is like a separating hyperplane. So that means it has to separate data, right? So what does that mean? Like a separating hyperplane or separating data, what does that mean? And so because we've run out of space, let me move here. And so earlier when we were like working with perceptron, we said whenever we got something like this, right, xn for any point n plus b equals yn, right? Now if like the signs match, then okay, this it's correctly classified, otherwise it's not, right? Now we can utilize both the left hand side and the right hand side and just like update this equation and still get the same information by writing something like this. Okay, yn W transpose xn plus b is greater than 0. All right, let's examine this equation. What is this equation telling me? Well, let's say if my yn is plus 1, right? And then like this thing here, the second term, my W transpose xn plus b, should also be plus 1 in order for this to be positive, right? Similarly, if my yn is negative, then this term within the brackets should also be negative in order for this term to be positive, right? So now if like my yn, this term is greater than 0 for all n's like 1, 2 and so on up to n, whatever number of n I have, there must be some point n for which we'll get a minimum of this, right? And let's say that minimum over like all these data points, that minimum n for yn W transpose xn plus b is the value of that minimum is rho, where rho is greater than 0, right? Because we are saying that this is greater than, like, strictly greater than 0 for all these n's. But that means like one of the points will have that minimum value that equals some positive value rho. Okay, and or we can like rearrange things and get something like this: yn w transpose xn over rho plus b over rho equals 1. Now, if we look at like this w transpose, this term first and then this term, well, these are, I would say, a new set of weights, right? And this equation is exactly the same hyperplane as the one that separated the data earlier. It's just like the weights are rescaled. Okay, so what we're trying to say here is that if there is any hyperplane that separates the data, there is an equivalent hyperplane, and geometrically speaking, of course. But if you like rescale the weights for that original one and do not change the sign, right? So then you will get that equivalent hyperplane. So both the definitions above are essentially the same, like here and here. These are the same actually. We're still getting the same, sorry, this one and this one. These are the same, they're giving us the same information. And why did we then like scaled our weights by some factor rho? That's because it's more convenient and that's why we use it. And regardless whether we use the first one or the second one, we're not changing what it means for a hyperplane to be separating, right? We just made it more convenient, and you'll see why it is more convenient in a short while. Okay, so let me write this definition of the hyperplane and when is it like a separating hyperplane. And so the definition here is something like this. So the definition says the hyperplane H, and now I'm defining the hyperplane as H, which is of course like defined by the W and the B. It separates the data, and it separates the data if and only if, right, this minimum of overall data points yn w transpose xn plus b equals 1. Okay, so again, any separating hyperplane in our earlier definition can be represented in this form by just like rescaling the weights. So we are choosing a scale for our separation essentially. That's all we have done. Otherwise, it is still giving me the same information as it was giving earlier. Okay, so earlier when we were separating the data, we could separate it with an arbitrary small value for yn. Let me show you what I'm talking about. This equation, right? So earlier we were creating this separating hyperplane with some arbitrary value so that it's like positive. Now we are trying to say that the minimum of this signal, and by signal I mean this entire thing on the left-hand side, must be +1. Now, what this means is if we compare the signal to 1, the further it is from 1, the more away you are from the hyperplane. So 1 sets an absolute length scale. This is a precise way of saying what it means to separate the data, because we were saying, let's define what it means to separate the data, and this is exactly what it means to separate the data. Okay, so now the second part of that question that we started to answer was, what about the thickness of the cushion? Now we have like a definition for a separating hyperplane. How about defining the thickness? What do you mean by the thickness? Okay, so even before, and because the idea of thickness comes from like when you hit the first point in some space, right? So let's try to understand how can we compute the distance of a point X to the hyperplane H, which is like WB, and let me go to the next slide. All right. So let's say my hyperplane is H equals WB, right? And I'm trying to find the distance of some point X from this hyperplane, right? And by definition, this is given by the absolute value of U, where U is the unit normal to the hyperplane, dot product X minus X1, where X1 is some point on the hyperplane. All right, let's quickly look at the geometry. What is this telling us? If this is my hyperplane, so we know that this is W transpose X plus B equals 0, and some positive region where it is going to be greater than 0, and some negative region where it's going to be less than 0, right? And x is some point here. I think we tried talking about it earlier, but then I just moved in another direction. So, of course, let's say x1 is some point on my hyperplane, and I'm interested in finding this distance. All right. So, if we can compute like um, something like this, like the normal to this hyperplane, and the distance from here to here, then this is like a vector, right? This is a vector whose distance can be found. And the way we find that distance is by finding like this times the dot product of the this distance, right? And you know that the dot product is going to take care of the angle because it's like the cosine between these two vectors. Okay, so if we can, so the important question is, can we compute this? How can we compute the unit normal to the hyperplane? So if we can compute this u to the hyperplane, then we can compute the distance, right? Now the weights that define the hyperplane, let's look at those, right? The weights that define my hyperplane, w and b, especially my w. So these weights are exactly normal to my hyperplane. They are normal or are in the direction of u, maybe in the direction of u, or maybe by definition we can say u is w is like it's a unit normal to the hyperplane and is given by this. Right, and again, why we are only considering w and not b is because we can have like infinite hyperplanes in this particular direction, but then the bias will help us decide which one to pick. All right. So this is a fact about the geometry of the hyperplanes, but let's look at like how, if you're not like 100% familiar with this, how this comes into picture essentially. So what happens is, let's say there is another point x2 on the same hyperplane, right? And x2 minus x1 is a vector in that hyperplane, of course. And we know the equation of the hyperplane, right? And according to the equation of the hyperplane, like we will have these two equations, which is w transpose x1 plus b equals 0 will be applicable because x1 lies on the hyperplane, and w transpose x2 plus b will be 0 because x2 lies on the hyperplane, right? And if we can subtract these and just like rearrange terms, subtract this equation from this, we'll get something like this: w transpose x1 minus w transpose x2 equals 0, right? And what does that tell me? That tells me that, and this implies w maybe dot product x1 minus x2 equals 0, which is, now if this the dot product of my weights and this like distance within the hyperplane is 0, this means my w is perpendicular to x1 because x1 is on the hyperplane, right? Because the dot product of like any vector in the hyperplane with w is 0, that means w is normal to the hyperplane. So my w over the norm of my w is a unit vector. Okay, so this was like some background information, of course. Therefore, of course, it follows that the distance between x and h can be given by, let me write it on the next slide. So the distance of x from the hyperplane h is this absolute value, which is w over the norm, which is like my unit vector, times x minus x1. Okay, so here it is. How can we find the distance between 2 points? Let me like rearrange a few things. This comes out, and this is going to be w transpose x minus w transpose x1. So this is the distance from x to h. Can we rearrange a little bit more? Not really. I think this will stay here. This can be replaced by w transpose x plus b. Not really replaced. I'm like adding and subtracting a b, and you'll see why I'm doing that. X1 minus b. That's it, right? And if I take out the minus here and take this thing common, we know that this is equal to 0 because x1 is a point on the hyperplane, right? Therefore, the distance of point x from h will be 1 over the norm and W transpose X plus B. Okay, so what is this W transpose X plus B? This is a signal that X generates on the hyperplane, and that X was the point whose distance I was interested in finding. This was my X. So this is how we can find the distance from some point on the hyperplane, and a few things, like a few observations why we are keeping this B separate. Why can't we just like have W with again W0 up to 1? And first of all, the first reason I think is quite evident here when we were deriving the unit normal definition, right? So the unit normal definition doesn't have the bias term involved. So it's convenient to deal with the weights only. So this was like simpler. Let me write it down here. So it was simpler to deal with, first of all, and that's why we said it's convenient. The second thing is this distance calculation that we did just now. That's why. Because like the numerator plays the same role as having the bias, like, but the denominator is just the norm of the regular weights. So W and B should be treated differently. The weights and the bias should be treated differently. And also in the geometry of the hyperplanes, weights will play a different role as compared to the bias. So weights are normal to the hyperplane, bias determines the shift of the hyperplane. All right, so we have something concrete, which is like the distance of a point X to the hyperplane H, and it's given by this equation here. And this equation is going to stay very important in the discussion of support vector machines. In the next video, let's talk about the thickness, like determining the thickness of a separating hyperplane now, given that we have this background information.